Hi, and welcome back to numerical analysis. So, what we've done so far is we've gone through and we've shown a lot of function approximation using polynomials. So we start off with Taylor series, and there we found the Lagrange remainder using Cauchy's formula for iterated integrals. And we showed that under some circumstances, Taylor series will actually end up converging, but we saw at least one example where it doesn't. Then following that, we went on and we did a couple lectures on function interpolation. There, we saw that if we match a function at particular points with a polynomial, then if there are n plus 1 points and the polynomial is of degree at most n, then the polynomial is uniquely determined. And then that leaves a couple things. That leaves us with just determining an algorithm to find that particular polynomial, and we saw three different ones that we could do. We had the Lagrange interpolating polynomials. We also use that for just proving existence. We have the Newton's method for interpolation, which involved divided differences. And then we had the straight linear algebra take, where we used the Vandermonde matrix in order to compute the coefficients for the polynomials. So, so what we're going to do is we're going to shift gears a little bit and talk about a different method of approximation, and this is with what are called kernel functions. And in particular, we're also going to talk about radial basis functions, which are a particular kind of kernel function. So, basically, what we're going to do is we're going to copy what we saw with the Vandermonde matrix, where we basically took a look at a system of differential equations, and it gave us a whole bunch of coefficients to find. Now, what we're going to be looking for is we have new functions that are not polynomials, but maybe an exponential function or maybe a Gaussian shifted around. And on each one of these functions, we're going to have weights. And so using interpolating conditions, we're going to have a whole list of different, we're going to have a whole system of linear equations through which we can use matrix inversion in order to find the weights for these interpolating, interpolants. So, I think typically what is done in a lot of numerical analysis classes is that they look at spline methods. And spline methods are good and they're useful. Basically, you just are doing a sort of interpolation with piecewise polynomials. And so it's not actually too far from what we're already seeing. The difference there is that you fix a polynomial degree, and then you basically switch to a new polynomial at each breakpoint. The issue there is that while that is very handy and it is used all throughout mathematics, so are a lot of RBF approximation methods and kernel approximation methods. Those over the past 20 years or so have, even 30 or 40 years, have really risen to prominence. And so this is sort of an easy entryway for a sort of a modern approximation theory that you can do. And an advantage that kernel functions have over that of splines is that while splines can get you really good convergence order, it's harder to translate them to higher dimensions. Whereas with kernel methods, the algorithm is actually unchanged when you moved from 1 dimension to, say, 20 dimensions. It's exactly the same algorithm. Now you need a lot more points if you're doing a 20-dimensional problem than you would for a 1-dimensional problem, but that's just a matter of data gathering. So kernel functions are actually used a lot in machine learning and data science, and so they're sort of the pivotal tool in doing support vector machines, and that's what really brought them to sort of the applied mathematics community. Where you see a lot of SVM type methods going back to, say, Vapnik and Shulkov and a bunch of other people back in the 90s, and then they've but nowadays they're used for all sorts of things. I use them in, say, pure mathematics and operator theory. I've used them in approximation theory, like what we're talking here. I've solved initial value problems with them from differential equations, and also PDEs. They are really good for collocation methods, which you don't know what that is, but maybe someday you will. And yeah, so it's something that's worth talking about. And yeah, I guess I can keep jabbering, but maybe eventually we should just go ahead and hop into lecture, and you can see what these kernel functions are. All right, so we'll go ahead and start lecture, and I'll see you on the other side.
Okay, so let's go ahead and get into this. So the idea is that we're going to be doing more function interpolation, but we're going to be using something that's different. So we're just going to call this lecture kernel interpolation. All right, so so basically we're going to have a different collection of functions other than polynomials, and this is going to be linear combinations of what we're going to call kernel functions. So so we're going to have a function. So we're going to say let k go from, say, x cross x to, or rather, to r, be a function of two variables be a function of two variables on a set x. Then k is called a kernel function. Kernel function if the following holds. Or say one of the following holds. So one, given any collection of points say x1 up to x, say m, in X, the matrix that we make like this. So you can say k x1, x1, k x2, x1, all the way down to, say, k x m comma x1. And up here we'll do the same on the other variables. So we're going to keep one fixed here and go to m here. And down here we'll go down to k xm xm. So this matrix is positive definite. What does positive definite mean? It means if you hit a vector here, transpose, and a vector here, then this holds for all v in, say, R, M. Right, so no matter how many points we get, so if we take, say, 1 point, 20 points, 1,000,000 points, we're always going to have this sort of positive matrix, and this is called the Gram matrix for the kernel function. There's a lot of reasons why it's called a Gram matrix. And basically what this means is that it is invertible. If it's a positive, well, here, let's just take off the equal sign. Sometimes they allow this to be positive semi-definite, but if we stick to strictly positive definite, then we're going to be a little better here. Okay, so we're looking for functions that satisfy this. And then there's another one. They can be written as this. So k of xy is equal to the sum I going from, say, or let's just say m goes from, say, 1 to infinity of psi m of x times psi m of y for a collection of functions, say psi m going from x to r, such that the sum of psi m of x squared is less than infinity for all x and x. And so these are called feature maps. So this is a feature map. So if I should also say if one of the following holds. It turns out that these two are actually equivalent. And one big reason for that is that this is sort of an inner product. And so a gram matrix is basically you construct out of an inner product of different collections of basis functions. And so you can easily show that if you have this, then you get this. And but going the other way is a little bit more complicated, and that would take a little bit of knowledge of Hilbert space theory. And basically we'd have to build a Hilbert space using this idea, and that is way beyond the scope of this class. Okay, so now let's talk about a few examples of kernel functions. Start with examples. And so my favorite one is the exponential dot product kernel. Kernel. Or it's also known as the Fock space kernel in a different context. But basically we're going to be writing kxy is equal to e to the x times y. And this is a kernel function for the set x is equal to r. Okay, how can we show that? Well, that's pretty easy to see. Basically, we can write e to the x dot y is equal to the sum of going from, say, n equals 0 to infinity of x to the n times y to the n over n factorial. And you can rewrite this as n equals 0 to infinity of x to the n over square root of n factorial times y to the n over square root of n factorial. And so then we have features, say psi n of x is going to be the sum from n, or rather psi n of x ends up being xn over n factorial, and the sum of psi n of x squared, n equals 0 to infinity, is the sum n equals 0 to infinity of x to the 2n over n factorial. And yes, that is less than infinity because this is just e to the 2x. Or rather, e to the x squared. So that's nice. Okay, so this is a kernel function. It turns out we can make another kernel function out of this. Let's see. Okay, so what we can do here is we can make up another one, and this is going to be the Gaussian RBF kernel. Here it's radial basis function is what that means. Okay, and so this is easy enough to make. What we do is we actually build it off of the exponential dot product kernel. So if I were to go ahead and start with e to the 2xy, and I multiply it on the left by minus e to the minus x squared, and on the right by e to the minus y squared, then I get this. I get n equals 0 to infinity of, say, e to the minus x squared times, say, 2 to the n, x to the n, y to the n over n factorial times e to the minus y squared, and can continue writing this as, say, e to the minus x squared. Now let's subtract a whole bunch of little bits. So we have square root of n, and we have root 2 times x to the nth power, and then this multiplied by e to the minus y squared times square root of 2 y to the nth power over square root of n factorial. So now we have our features are written as psi n of x is equal to e to the minus x squared times square root of 2n raised to the nth power divided by square root of n factorial. And you can show, if you'd like, that the sum of psi n of x squared is less than infinity. It's exactly the same as what we have up here. The only difference is they end up having this term that you factor out. So what does this give us? This actually ends up giving us e to the minus x minus y squared. And this is Gaussian RBF kernel. So we can also write them out with a few, we can add a parameter, the parameter mu. And so just to rescale them, and this is important when you're talking about different kinds of data. But basically we have the exponential dot product kernel, and we have the Gaussian RBF kernel, e to the minus x minus y squared over mu. Okay, and so these are two different kernels. So exponential and Gaussian RBF. Okay, so big questions then are why are these called dot product kernel and the Gaussian RBF kernel? Well, here, if we switch from, say, R to Rn, then basically x dot y becomes xi times yi, I going from 1 to n, and this is the dot product. And yeah, and nothing else, and that's still a kernel. And over here, we end up having, so say, switching to Rn, then we write e to the minus the sum of xi minus yi squared divided by mu. And another way to write that is e to the minus, we put double bars to indicate the norm in Rn. And that's what we have here. Okay, and so that's what we got. So why radial basis function? And that is basically because if we choose to fix y here, then the function that we're going to get is going to be centered at y, and it's going to decay as x moves away from y, right? And the dot product kernel is a little bit more finicky to think of, but just basically in Rn we have the largest contribution when x and y are aligned, and the smallest when they're perpendicular. So, but yeah, that's harder to draw. but yeah, so e to the x dot y over mu is largest when x is parallel to y, and smallest when x is perp to y. Okay, and when x is perp to y, it just gives you 1. All right, so yeah, so that's 2 different kernel functions. So what is our goal? So our goal here is given a function f, and we're just going to talk about it over AB like we have been. We would like to find a function, well, I should say not only a function, but I should say at least and a collection of samples, say xi, comma, let's say yi, I going from 1 up to capital M. So we would like to find a function s that let's call this Sm, such that we can write this as a sum of I going from 1 up to M of Wi times k of x against xi. And yeah, and so we would basically like to be able to describe it as a linear combination of kernels that are, quote, centered at our points. And so here we call x1 up to xm the support points for our approximation. Okay, so now we would like to come up with some sort of algorithm in order to find this, and it turns out that if we approach the this problem just the same way we did to develop the Vandermonde matrix, we're going to end up with something nice. So let's go ahead and take a look at that. And so here we're going to have, so we know, for instance, that we want s of xi to be equal to yi. In particular, we want s of x1 to be equal to y1, and s1 is supposed to be w1 times k of x1 comma x1 plus w2 k of x1 x2, just evaluating all these guys at x1, and keep that going well, all the way up until we get to wn k x1 xn m. Wait, where'd that go to? Capital M. Boop, capital M, capital M. Right, so that's the first one. And now we do the second one, x2, which we say should be equal to y2. And this is going to give us w1 times k of x2, x1 plus w2 of k of x2, x2, plus all the way up until we get to wm of k of x2 comma xm. And then we get Sm of x3 is equal to y3, which is equal to w1 of k of x3 x1 plus w2 k of x3 x2 all the way up until we get to wm of k of x 3 comma xm, right? And I'll just do this last one. Sm of xm is equal to ym, which is equal to w1k of xm x1 plus w2k of xm x2 all the way up until we get to wm of k xm xm. All right, so now we have a system of equations. What we want to do is we want to I can't spell right now. Want to find wi, and this is linear in w. Right? So what we can do then is we can recognize that basically if we take this first row and we take each of these pieces and throw them into a matrix, then this is what we get. We get k of x1 comma x1, k of x1 comma x2, all the way up until we get to k of x1 up to xm. And then the next line is going to give us k x2 x1, k x2 x2, all the way up until we get to k of x2 xm. And this we follow down until we get to k xm x1, and this follows all the way down here. We have k xm xm, and this is being multiplied by w1 w2 down to w capital M. And so that represents all of this stuff. And on the other side, we have our outputs from our samples. So y1, y2 down to ym. And there we go. Okay, so we have basically written out our gram matrix. And if you remember back at the definition of kernel functions way back when, we're told that this is positive. So if we move forward, then basically what we see is that this is invertible. Okay, so basically this is what we find. If we call this, say, g times w vector times y vector, then w vector is equal to the inverse of g hitting against y. Okay. So, now, again, we want to know when is g invertible. And basically it's when xi is not equal to xj for I not equal to j. So distinct points. Right, and so there we go. So, yeah. So the rest really just comes down to linear algebra and inverting this matrix in order to find these interpolating functions. And yeah, I think that bit is best left to a MATLAB lecture, and so so we'll just stop here and we'll jump into a MATLAB at midnight segment to wrap it all up.
Okay, so that's kernel interpolation. Kernel approximation, and basically what we saw is that we can develop an algorithm using the same exact reasoning that we used to find the Vandermonde matrix. Now the difference with the Vandermonde matrix and this Graham matrix that we made is that the Vandermonde matrix we can prove is invertible by using the Leibniz form of the determinant. But sorry, I did just eat lunch, so I'm burping a little bit. Anyway, also crashing a little bit. I'm really tired. But as far as the Graham matrix, we had used a little bit of different linear algebra reasoning, where we showed that the Graham matrix is actually a positive matrix, which means that it doesn't have any zero eigenvalues, or at least under certain conditions. And so, so that's where that leaves us, and so it ends up being invertible, and you can find weights by using an inverse. In either case, those are kernel functions, and yeah, I think we're going to end the approximation function segment here, and next, I think we're going to go into doing derivatives and differentiation integration with numerical techniques, and we're actually going to leverage a lot of this polynomial interpolation that we've learned already, and in establishing a lot of the formulas that we're going to see. Man, I'm tired. Anyway, yeah. Anyway, thanks for listening, and yeah, I'll see you next time.